Okay, well, it's a great pleasure to welcome Justus Lagerland. Today he's going to give us a Blackboard talk, which hopefully it's experimental, hopefully it'll work well. It'll work well for us here in the audience anyway, but hopefully it will work for the online people. Justus, from the news, he's just taken over his head of department there.
Officially, yes.
So he's going to tell us about fusion rates. And he has promised to keep his introductory at least at the beginning. So I'm looking forward to that. It's up to you.
All right. So thanks very much for inviting me. I promised that it should be pretty introductory at the beginning, but nevertheless, I talk a lot about this kind of stuff. So feel free to ask any questions because I'm likely to just skip over something somewhere. So also I must apologize in advance that this talk may not be as well organized as might be expected because my week has involved, for example, the night on the beach at Schiphol Airport and various other things. So, but I will do my best. All right, so.
This is going to get in the way at some point.
Yeah, take it away. So introduction to fusion rings. Fusion rings. Right, so first of all, before I say anything, I must of course acknowledge the people I've been working on with this and maybe give you a few references. It's going to be a very biased introduction and of course we are contributing to my own paper. So please have a look at the main paper. I think probably this is relevant to 2205 15637. That's literally called low rank fusion rings. This paired vergelijking. PhD student in Belgium. And he's actually the first author, of course. And then there's also 2202.0807. And with Aaron, who's in the audience here. Aaron Conlon. That's about particles fusing and braiding on wire networks or on graphs if you prefer to be more mathematical about it. I have another paper about fusion rings out, fusion stuff out more recently with Steve Simon, so I don't think that will get mentioned, but I have time left, you never know. Okay, so so first of all, I need to define fusion ring. What is a fusion ring? I'm not going to immediately give you a formal definition, but once I tell you, then what would be necessary, and you want to know what it is. So the idea is that we want to describe some situation where we have charges of some type or other, and it's helpful to keep in mind the spins, spin 1/2, spin 1, spin 3/2, etc. And these charges can fuse together, which doesn't necessarily mean you actually push them together, but you can, from a distance you can look at them and the two charges have one overall global charge. So 2 spins 1/2 can, for example, look like spin 1 or spin 0. So now with the fusion ring, we have charges and we label them A, B, C, etc. Usually we require that there's only a finite number of types of charges. Finite number of types. It's called this R, and this R is called the rank of the fusion ring. Okay. Well, we can, if we want to, we can make linear combinations of charges. Just think of that formula at the moment. So these actually form a basis for a vector space. relations. So some over all the possible A, lambda A times A, where these are complex numbers, or if you like, you can use any field you like, but stick with complex numbers. So now we have a vector space, so we can add these things, multiply them by scalars, etc. Okay. And then we are able to multiply the charges or to fuse the charges, and for that we have fusion rules. Combine charges. For fusion rules, and a lot of the time people will just talk about fusion rules and not about the actual rings. So if we have a chart A and a chart B, then you can say that these combine as a sum over possible fusion outcomes C, N, A, B, C times T. And these N, A, B, C's here are just integers. So you can think of them as a number of different ways I can combine A and B to C. Later we will interpret these as dimensions of some vector spaces, so then it's clear why they're integers, maybe it's not so clear yet, but and C positive integer, non-negative integer numbers. Okay. And like I said, a good example here is to think about spins. Spins. So the bad thing about this example is that there are infinitely many different possible spins. 0, 1/2, 1, 3/2, etc. So we'll fix that later, but for now let's not worry about it. And then we have things like 1/2 times 1/2, 0 plus 1, because if we add two spins, spin 1/2, we can get spin 0 or spin 1. And then we can interpret this now as saying that n 1/2, 1/2, 0, and n 1/2, 1/2, 1 are both 1, but for example, n 1/2, 1/2, 1/2 is 0, because that's not a possible fusion of two spin 1/2. Okay, so this is always handy to keep in mind. The whole point of the first part of the talk is to give you some examples of fusion rings, so you don't feel like I'm talking about an empty set. Actually, this of course represents the Clebsch-Gordon series. Gordon decomposition. And we do it for general spins, and then of course we have spin J1 and spin J2. They can add up. Well, they have to be at least the difference in absolute value, and then the other terms would be J1 and J2 plus 1. That's the whole spin, so a bit of extract. Then plus 2, plus 3, etc., all the way up to the maximum spin, which is J1 plus J2.
And sorry, so in the Clebsch-Gordon example, all the n's are 1.
Yeah, that's right. Yeah, but it is possible to have an integer not 1. I'll give you an example.
Okay.
Okay. So good. So now I haven't said everything I require of the fusion ring. I'm still defining it. I also require that fusion is associative. So require associativity. So A times B times C is A times B times C. Now this is physically a very appealing rule, because basically said, well, if I have A and B sitting somewhere, then I can think of their global charge, but then I can also think of the global charge of A and B C together, and That's really what I'm making with this triple fusion. So it shouldn't matter if I thought of it this way or as these two together first. I mean, in the end, we're just looking at the possible global charges of the triple, so it should be fine. Okay, of course, this also makes our vector space into an algebra now, because suddenly we are able to multiply these arbitrary linear combinations by just linearly extending the product on the basis, right? Then the associativity makes it work. And we have another requirement. So now it's also vector space A. Now we have an algebra space A an algebra or a ring. If you want to be a bit more careful about it. And then finally, we also require that to have a vacuum charge, a trivial vacuum charge. That's
Yes.
yeah.
Are you going to, I mean, in the examples you've taken, you have A times B is equal to B times A. And
Yeah.
so are you going to assume that the NAB are symmetric?
Yeah. So I will actually show examples where NAB is not symmetric. But it's a good question, because if you think about really in two dimensions here, like on the board, then you think, well, I can just put A and B the other way. And why wouldn't they be? Then I would expect the total charge in this region to remain the same. But I also want to be able to think about situations where the particles are sitting, for example, on a line. Now there's actually no way to exchange these without making them pass through each other somehow. So then maybe they can have a fusion that depends on the order. Okay, so we have a vacuum charge, usually called 1, but for spins, this happens to be unfortunately 0. So it's one of those things you always run into, could be 1 or 0. But the important thing is that it's the unit of the algebra, so we get 1 times A times 1 is A, all A. So, yeah. It's a unit of the algebra. And then it has to have some special properties with respect to the vacuum. So the idea is this charge is basically like there's no particle or actually no charge, so it doesn't matter if I have that in addition to something else, right? But I should also be able to create and annihilate charges. If I start with no charge, I should be able to create 2 charges. And if I have 2 charges, I might be able to annihilate them. So for every all A, we have A in this. All A in this basis, we have a bar.
The vacuum, I don't know what the vacuum that means a unit of A.
So the unit of A. So
The unit of way. I understood the meaning of A, but I don't understand the meaning of the vacuum charge 1.
oh yeah, so I'm just saying among these charges A, B, C, etc. These are special. They're the basis that I created the algebra from. There is a special one which we might indicate as 1. For spins, this is the one we call spin 0. But usually you might call it 1.
But you could have done the spins in terms of the dimensions of the.
Yeah, we could have done that with the dimension. Yeah, could have done that. But the point is that that one acts as a unit. So it means that if we fuse 1 with A or A with 1, then nothing changes because it's essentially no charge. But we need that in it to make it all work. Yeah. And then we also want for every A to have a sort of anti-particle charge A bar. So that take A times A bar. Then then this would have the vacuum charge in it plus potentially other things. But it will have a unique way to annihilate the vacuum, and the same thing for A bar times A. And in fact,
Under the dots decision that we got to.
I'm not immediately requiring that in there, but but I don't know any examples where there are. Yeah, and in fact we require that if you look at the these fusion coefficients and AB1, that is just delta A bar, which is of course effectively the same thing but more compact. Okay, so and if we have these things together, then we're almost there, but actually I want to require one more thing before I want to call this thing a fusion ring, which I think is quite reasonable, and it's sort of saying, well, if we can fuse things, we can also split them, right? And the fusion and splitting should be somehow compatible with each other. And there's a condition for that called Frobenius reciprocity. Now, this term is used in many different places, so but here it means the following: compatibility of fusion and splitting. I think this is most easily explained as a little diagram. So let's say, well, we have A and B, and they can fuse to C. Think of this as time going upwards, they fuse to C. So this means that NABC is not zero. So if this exists, then well, this probably should also exist. But we could say this A actually is created as a pair with an A bar. Here, in principle, you have the units, but you don't have to worry where that comes from. You can always sort of think as the unit is no charge. So then it fuses with this B here to C. But we want to be able to ignore these kind of details in terms of what we want to think of this as just, well, we see that the A bar and the C come together or are split off together from this B, right? So we can also think of the diagram as there was a B, and at the end there's an A bar and a C. Okay, some stuff happened in between, but so that means that you have this. Then we better also have this vertex in the first place. A bar but then if we can split the B into an A bar and C, we could also have that an A bar and a C can come together and form a B, right? Otherwise, we would have consistency of braiding with fusion. So in the end, this one, of course, comes with in this many ways, and A bar C. So we require that and A bar A and C equals to N A bar C B. Now we can do the same thing on the right hand side. So we could, instead of making A appear this way, we could make B appear instead of B bar on the right hand side. On the same set of ideas, and then we would end up with N B bar A, so that should also be equal. And imagine B bar going there, C bar A there. And we can also iterate this. So we can now say, okay, well, we can now put the C and make a C in a C bar on this one. And so we end up with 6 equalities here. So N bar B bar A here, and and finally the n bar, a bar, b bar. So now this is for yes.
Did you get the third one?
The last this one or this one?
No, the third one on the picture that you drawn.
Oh, this one here.
Yeah.
Yeah, so also what I'm saying is that, well, if you want to think of this as some kind of physical process, if you just look at this one, they've only started with a B, and then, okay, some stuff happened here, but at the end we have an A bar and a C. Right? So the B split into an A bar and a C, we can sort of course grain it and say that there should be a vertex in this theory that allows a B to split into an A bar and a C.
So we are not starting with A and B. I thought we were starting with A and B.
Yeah, what I'm saying is that
So you're assuming time reversal symmetry. With regard to the lower horn.
it's a sort of locality in a way. So what I'm kind of saying is that this A here could have come from a pair that was created at some earlier time of an A and an A bar. If I bring the A bar back into the picture, then it actually looks like an A bar going at the top. And this A is now this intermediate thing.
So we are going back from.
But the second picture is not starting from an A and a B, it's starting
Oh,
from a
it's
B
a
and a
different
Y.
one.
Yeah, it's
But
different.
it should be the first one.
No, you're just using the first one.
The first one, this part of it. But then I say, well, this A here that could have emerged from a pair like that, because I'm allowed to make this pair in the theory already. And then I just require that if you make this picture, then you should also have this vertex.
Yes, can I ask about the equation at the bottom, the fourth one? You've got an NC B bar A upstairs and then an NC bar A B upstairs.
Yes.
Yeah.
There could be.
I'm just looking at the first one, you send A to A bar, and interchange B and C. So with the NC B bar A upstairs, but send that C to the C bar, is it not B bar upstairs?
Yeah, I think you're right. Yeah, you're right. The C goes to C bar, and B bar goes there.
Sorry, just one more question.
That's actually what I had here also. This will be there.
Is this to show visual similarity with button diagrams? Something better, I guess.
It's more than a visual similarity. It's just that I didn't include any information about momenta or anything like that, but in principle you could include that in the labels. Of course you want to find a number of labels then, but but it's the same idea. That you have some great. So that in principle concludes the informal definition. Now, of course, you can roll this up into a proper definition and say a fusion ring is a unital ring with a special basis, and ABC, etc., such that the structure coefficients are all integers, positive, with non-negative integers, and a few other things. There's an involution, which is this bar, and then you have those properties over there. But I think if I had said that at the beginning, nobody would have probably got much intuition out of it. So hopefully you can reconstruct that now, or you can look it up. I have references for formal definitions. So people that are, I think one of the earliest papers that really looked at this more seriously is the paper by Jürgen Fuchs, the ring idea of fusion rules. Progress in physics or optical fusion. And that was in 1994. 42. 1994, and more modern achievements in the editing of wrote a book titled Tensor Categories, published by the American Mathematical Society. 15 or 14, 20, 15. Okay, so now that we have this, the first thing that is interesting to note is that if the particles are self-dual, which can happen, so it's totally allowed for A to be equal to A bar, and it's called self-dual. This happens in particular for all spins, because spin 1/2 goes with 1/2 to the trivial spin, and same for all the other ones. So if this happens for all particles, which is a significant percentage of all fusion rings, then we see that NABC is equal to NVAC here, and the fusion is actually commutative because well, it's symmetric in the left and right thing is totally confused. So you will.
It's easy to see that A bar is unique.
It's required. It's a requirement.
No.
In some cases it's easy to see, but I don't know if it's in general what easy to see, but it's usually required as part of the dimension. It's sort of low. So if we want to make any non-Abelian fusion rings, then we better have non-self-dual particles. Okay. Right, then I have some feel about how it's natural to think about particles that are self-dual. For example, because they're on a line, but also because they might be attached, for example, to a line. So you might be actually in 2 dimensions, but the particles are sitting here, but they somehow are attached with some string to a boundary. Now if I try to exchange them, the strings will come along and I will still be able, I will be able to see the difference between A being attached here and B there, or attaching the other way around. Like this. So you have to go around. So this wouldn't be the same. All right, it's not math, this is just a picture, but you can do math about it. Okay, so finally some examples, because I haven't given you any actual example yet, because the spins were there were infinitely many of them. Oh. So the first one, SP2 is level K. So this is like spins, except we only have spins 0, 1/2, 1, etc. up to spin K over 2. And it's a level K. It's also connected to a germ science theory where this K plays a role, but it's unimportant for us at the moment. Now, of course, because we have only finitely many, we have to modify the fusion, because otherwise we could just, with this 1/2 fusing more and more of them, I could make arbitrary high spins, and I wouldn't want that. And the modification is kind of nice. Now we have to take 1 times K2 is sum of J running from, well, the minimum is the same as before, so this is the absolute difference. But we don't necessarily go up to the sum, we go to the minimum or either the sum of the two, or k minus the sum. So if this is not something that seems intuitive, one way to think about it is adding these things on a circle. If you have a circle of circumference k, and you add things of length j1 and j2, then either j1 and j2 don't reach more than halfway around, then this is just j1 plus j2. But if they reach over half, then the shortest route here is actually this way. That one, of course, now k minus j1 minus j2 distance over the circle. So that's how I remember this in way. Okay, and this also helps maybe to convince you that this is associative, which I'm not going to prove here, but it's a thing for you to check if you haven't done before. And it's also good to look at a few special cases quickly. So for k equals 0, it's trivial because then we only have spin 0. Usual 0 times 0 is 0. Okay. For k equals 1. Now we have spin 0 and 1/2. The only interesting fusion rule is the 1/2 in itself. It's now 0. Normally we would get 0 plus 1, right? But now we see that this fusion rule is telling us the minimum of 1/2 plus 1/2, which is 1, and 1 minus 1, which is 0. So we can only go up to 0. So it's plus 1 is okay. We see that this is just like I said, 2 addition.
Can I ask a question?
Go ahead, Bob.
Can you hear? Okay.
Yes.
This labeling things are numbers, is it? Complex numbers, A, B, C, D, and so on. They are finite number of complex numbers, is it? Because, am I right?
Yeah. So
when you write A cross B equal to the n times the coefficients.
Yes, in this case, the ends are all 1. The only ends that appear are all 1 on the right hand side.
Yeah, as you took care, I'm not bothered. In general, are these A, B, C, D, and so on complex numbers or abstracts?
The ends are in general integers, but they can be greater than 1.
I think he's asking
Ends are integers, but what about A, B, C, D, and so on?
the modules,
The charges.
the challenges.
From the very beginning, you had A cross B equal to something.
They're just abstract labels at the moment. They don't have any meaning. But of course, for spins, you would think of them as representations of SU2, and then the cross becomes tensor of the representation.
Then what is the norm on this algebra? You are writing max and min and so on. So this is for example, in quantum field theory, one can think about it as the reduction of vertex operators. So there, what is the norm? You're writing some star operation, but what is the norm? You're writing max, minimum, and so on. So there is a norm. Is it a C-star algebra or what?
He's asking if there's some, because he's thinking that there's some norm on the algebra, because you have a min in the top of the sum. But at this point in this example, they're just numbers.
Here,
And you didn't ask for a norm on the general abstracts.
in general, there's no norm or anything on these abstract labels, but here it's just a convenient way to describe the allowed channels, because we've labeled them with numbers, so we can say, oh, the maximum of these numbers is pure algebra.
But they may not be numbers. In quantum field theory, they are not numbers.
The representation, in this case, the particles or the charges are labeled with numbers, which helps me to write formulas like this, but in reality they aren't actually numbered, they're just labeled with these numbers.
It's a degenerate notation.
Yeah, it's kind of it's not the best notation, but it keeps contact with spin, so that's hopefully that helps some people.
It's also not correct in the case of spins because there are vector spaces that you're tensoring.
Yeah.
And then you're just labeling each vector space by 1/2 and 1.
Yeah, sure. Yeah. But also, this is no longer the same usual anyway. But it's a nice way of introducing things.
Benjo, sorry, can you explain? I can't hear him very well. What
Sorry,
is the answer? Is it a star? Is it non-star algebra? In general,
Not necessarily. It's an algebra, and I would think of them as vector spaces on the left. J1 and J2 with the tensor there are vector spaces. You might write them with a bold label, and the label on the vector space is what's on the sum.
Yeah. So at the moment,
That's it.
these are
the general notation.
Yeah, it's a funny notation. I mean, these J's at the moment are just abstract objects that I'm using to build an algebra. But yeah, they're just labels. But because the labels are also happen to be numbers, not the objects, but the labels are numbers. That's why I can write this notation to sort of summarize the fusion of these objects. But
When I do things, I like to call the one to the left, like there's gamma J1, so gamma J2, and then gamma J, it decorates it a little bit more.
yeah, I could do that.
Yeah, but it's clear in the context.
Hopefully, it won't cause too much problems later. It's just an example anyway. Yeah, I wanted to show one or two more here. So I said that the cake was one. We basically have two objects, which I've labeled 0 and 1/2. But if you want to, you can label them 1 and A or something. And then this is just A times A. One is also unfortunately double by a number. Maybe I and A. Okay. So cake, I'm going to just persist for a little bit. So for cake equals 2, we have 3 objects with 0, 1, 0, 1/2, and 1. And I can make their fusion here. Zero, 1/2, 1 times 0, 1/2, 1. And in this case, well, of course, 0 times anything doesn't actually change. So, we're doing 3 again. Yes, okay. Yeah. And then 1/2 times 1/2 would give you 0 plus 1, which now it works again because the 1 is still less than 1 minus 1/2 plus 1/2, 2 minus 1/2 plus 1/2, is equals 2. And then, but 1 times 1/2 will give you only 1/2. Normally it would be 1/2 plus 3/2, but this is too big and falls off. Same here. And 1 times 1 would normally give you 0 plus 1 plus 2. But the 1 and 2 are both too big, so you just end up with 0.
No.
And
the one is not so big.
2 minus 1 minus 1, 0.
Oh, the middle is 0.
Yeah. So, so you can only get 0. And then this one is a very well-known one. Often people write 0, 1, and 1/2 of 1 instead of 1 sigma psi. And then they call this the Ising fusion ring. And then, of course, the only interesting fusion rules here are sigma times sigma equals 1 plus psi, which is that one here. And sigma times psi equals sigma, which is that, which is also psi times sigma, and psi times psi equals 1. Okay, so that's an important example.
And is the first one, is there a name from your first equal 1 example?
Yeah, yes. Well, this is just that two, but there are different types of that two. It's kind of too obvious to have a special name. Yeah. And then another example, which is follows immediately with this one. It's called ESU2 level K. And this is just take SU2 level K like we did here, but keep only the integer spins. So throw all the half integer ones. Just the integer spins from SU2 okay, where integer of course only applies to the label. So for example, that means that the rank of this, the number of different types, is k over 2 with k is even, and k plus 1 over 2 with k is odd. That's half as many as you might think, because half the odd ones, the half integer ones are thrown out, and you see that ESU2 level 1 is trivial. Only one object. ESU2 level 2 is actually another Z2, because basically we only keep the 0 and 1 from this table. You see, well, 1 times 1 is 0 here, so that's Z2. But PSU2 level 3 it's then starts to become interesting. And this is called the Fibonacci theory of programming. So at level 3, we would have, well, for SU2, there's 0, 1, half, 1, 3 halves, but now we only keep the even ones, the integer ones, and then you end up with 1 times 1 is 0 plus 1. So suddenly now you have two different fusion channels. And it's called Fibonacci because this naturally leads to the Fibonacci sequence once you start to iterate. You make 1 times 1 times 1, 1 times 1 times 1 times 1. The number of zeros and ones that you end up with are all Fibonacci numbers. So this is a nice exercise, but I'm not going to do it now. So now we see that we have two examples already of different fusion rings with only two dimensions, only two basis elements, and you might ask, are there more? And in fact, it's pretty easy to write down all the fusion rings with rank 2. All rank 2 fusion rings. Well, you have two basis elements, two charges, one, and let's call the other one tau. It's traditional to call this one the Fibonacci theory tau, so then you like tau times tau equals over 0 becomes 1, annoying, and 1 is tau. So in general, we would end up with having, well, in principle, we have fusion coefficient n111, n tau 1 tau, n 1 tau tau. But these all have to be equal to digit 1 because of the definitions we already made at the start. With the vacuum charge, and then finally we only have n tau tau tau. But we can choose this to be whatever we like. So it's called n. Free. Choose whatever you want. And the reason is because, well, there's associativity is very boring in this case because tau times tau 1 plus n times tau. Is that for me or?
I think someone's mic is probably on mute.
Well, associativity looks at things like, 1 times tau should be equal to 1 times tau, for example. But this is automatically true because this is by definition equal to tau. And with tau times tau, and this is by definition equal to tau times tau because the 1 doesn't do anything. So, associativity is really true. So that's all the fusion rings of rank 2. Unfortunately for us later, when I say later, probably after this talk, but it turns out that the ones I showed you already are the only ones that are really interesting. So the ones with n larger than 1 are only interesting as a way to exclude certain things from being physical. They aren't actually physical things. It means there's no tensor category for the ones with larger n.
What's the obstruction?
You have to try and solve the pentagon equation, and then it turns out it doesn't work. But I can't tell you a short answer.
It's given that it doesn't work.
Yeah, but there are papers that prove this for all n, so it's not like we are unable to write down an instruction. I just can't tell you immediately. But there's no solution to pentagon. That's the issue.
Is it that there is no solution known, or that there's a result?
There's a result that there is
And
none
cannot
in this
be
case. Yeah. But I don't know exactly how it works. Okay. It's very special for this case anyway. All right, so then there's a few other examples that I have to tell you because basically there are large classes of examples, and they sort of make it obvious that this includes too many things to be able to sort of just classify all the fusion rings and also includes interesting things. So first thing, irreducible representations, irreducible representations of a finite loop. The tensor for the decomposition. So if I have a finite group, any finite group, then I might have representations by I by j. These are finite dimensional representations. I can take the tensor product, and then I know that there's a kind of flat coordinate series for any finite group. I can take a direct sum of the product of the vector spaces of these. I just said the direct sum is irreducible representation, and again, where any irreducible representation can occur an integer number of times. This is now my integer nijk. Here. And so every finite group gives an example like this. That's a nice example. These are always Abelian. Then a nice, and in particular, this is particularly good because we can immediately give an example of a case where multiplicity happens naturally. So, for example, you can look at the group X12, group order 12, which is rotations. It's a distinct group of rotations of a vehicle. This is 4 irreducible representations. Which are conventionally labeled 1, J, J bar, and alpha of dimension 1, 1, 1, and 2. The three-dimensional representation is just the actual three-dimensional matrix rotating the tetrahedral. Okay. And the one-dimensional ones are representations of the Z3 coordinates. So this there's a Z2 times Z2 normal subgroup in A4 for 4, which is 180-degree rotations. You can divide that out, then you have a Z3, which is obviously something to do with rotating the 3 planes around this vertex into each other, and that Z3 is fine. And we can do so in one-dimensional representations. That's these 3 representations. And now, if you take, for example, alpha times alpha, this naturally divided 1 plus j plus j bar plus 2 times alpha. So there you go. Which it has to be like this because this is 3 times 3-dimensional, 9-dimensional, 1 plus 1, and then you have 6 dimensions left. And you can't have the 1 more than once, so you kind of forced to do it like this without really thinking about it. So there we are, and you see that. And alpha is 2. And this occurs very frequently with finite loops. Okay, so and I think this is actually the simplest example of a fusion ring that has a multiplicity and can be made into a tensor category. Okay. Right, then we can make the finite loop itself. So charges are just elements. It's made by elements of the group. And v times h is the h, and this is the group product. And group product is obviously associated, because otherwise it would be a group. And then we have G bar, which is the inverse in the group. And for the 1 is the unit elements in the group, and satisfies all the actions we want. And this can obviously be non-Abelian very easily because the group doesn't have to be Abelian. But the group, yes.
We're in that last example, or is the plus 1 plus?
There's no plus. There's no plus. So in this case,
Oh, right.
yeah, there's always a unique fusion outcome. But
Oh,
kind of boring, but as you see that it's included as a possibility.
Yeah.
Yeah. So basically, n d8k is delta d8 k in this case, and can be non-Abelian. Maybe one more example before we're going to talk about some ways to find fusion rings. Is the so-called Danbari Yamagami. Here. And what this does is it says, okay, I do the same with the group, but then I add 1 extra charge, and I call that tau. For example, or maybe let's call it tau. And then say, okay, well, of course, just like before, times P1 times P1 P2, G times tau, and it's also tau times G. So everything is brings tau back to tau, and tau and tau is going to be the sum over all the elements of the group. And actually, I can generalize this a little bit, but I could also n times tau, but then you can involve some variable value. If you work it, it still works, and it's still associative. And for example, here we take the group to be Z2. This actually turns out to be the Ising model we looked at before. With one psi over there being the group Z2 and sigma being the tau. If I take Z3, then it's something slightly different, but it's easy to make these, and they can also be non-Abelian. But it turns out that you can't make categories with them if they're non-Abelian. Which I can actually show, but probably not in this hour.
In the finite list necessary in the example finite loop, how about the general is it fusion?
So I've required in the definition that this should be finite, but of course, in principle, you could do most of these things with infinite things, but then eventually you will want to calculate things in various categories based on this, and they will probably fail if this thing is not finite. Or well, you need stronger restrictions on it then to make various sums converge and things. So at the moment, I'm just making everything finite, but I would certainly encourage people to look at infinite examples and just see how far they're getting, because you can do many of the things. Right, so this so now, next thing I want to do, and this actually starts to touch on some of our own research now, is to actually find fusion rules. I'm running out of time, so
We are always relaxed about that. We are a research institute, so we don't worry about teaching.
all right, excellent. I can keep going for maybe at least another hour, so no problem. You might want to have a comfort break or something. Anyway, right. So the first thing is, if we want to just, I showed you a bunch of fusion rings just to show that they exist and they're interesting and there are loads of them. But it's a natural question to say, if I fix the rank, the number of types of particles, how many are there? Can I list them all? That would be useful. Like with finite groups, you also want to say, well, try to understand the groups of 4 with 4 elements and 5 elements and 6 elements, etc., like that. First of all, right? This turns out to be really hard. So the brute force approach, but it's trying to find the fixed rank. And let's also fix the maximum multiplicity in the whole ring. So M minus 1 over A, B, and C is N, A, B, C. So we know they have a maximum. Then the naive thing would be to say, okay, well, just propose A, C, some value 0, 1, etc. to M for all ABC. Right? And then check afterwards if it's associative pivotal and has these what's it called? Non-Frobenius reciprocity rules, etc. This is a terrible idea because, as you can see, NABC, there's 3 choices of R. So that's R to the 3rd choices. But then for each of those variables, you have n choices. So, or n plus 1 choices actually. So that gives n plus 1 to the power r to the third things to check. This goes up very badly. I suppose that r is 5 or something, and that's 125, and then if m is even 1, it's 2 to the power of 125, so let's forget about it. Okay, at least it seems so. So there's a few things that we can do to improve things without even looking very hard. So first of all, we fix the joules. So we can just say that the self-dual particles are first. So we have A1, A2, etc. It's called AS, the self-dual. These are the first S particles. And then the rest of them are in pairs. V1, V1 bar, V2, V2 bar. Bar, and together there are of course still RBs. Pairs. Give them. So that already helps a little bit, because one of the problems here is that every permutation of a fusion ring is also perfect good fusion ring, which means that you find if you have a fusion ring with 10 particles, you find it 10 factorial times. Right. So also we might as well say that A1 is just 1, the first one at the start, which helps, and then this will fix and A1 and A1 and more AB for all AB. So suddenly now we don't have to worry about ends that have a 1 in them somewhere anymore. So that makes this m plus 1 here go to m. Helps a little bit. Now we can do a little bit more. So we can also fix the orbits on the pivot thing that we were thinking about. They have the same value. That reduces the number of variables some more because the variables of number are in ABC. So that's the most factor of 6, right? So in ABC is actually the same variable as n, A bar, etc. And the most factor of 6 is reduction in variables. But for small numbers of particles, that can make a big difference. For small number of charges. In fact, if you do this now for rank 3, for example, and you say, okay, well, it's rank 3, but 2 of them are not self-dual. So it's 1 and a pair. And then you use this, then there's actually only 2 variables left. If you look carefully. Whereas naively there would be, well, 3 to the third would be 27, and then after this would be still 2 to the third would be 8, but then after this would be only 2. And then actually you can solve the associativity equations very easily, and you find that there's a unique fusion ring for that case, and it's actually set 3. So now easily r equals equals 3, with p, the number of pairs equals 1, and find that there's only the 3 fusion there. Actually, so and that only has multiplicity 1, but actually works for all multiplicities in this case, so no other ones.
You might hope to solve the case where there are no pairs, where you just a self-dual.
That turns out to be the most difficult case.
Oh, really?
Yeah. Because you get the least opportunity to somehow break the symmetry. So even though the certainly for small numbers of particles, that somehow there are way more solutions in the end which are self-dual than which are not self-dual. But the not self-dual ones are interesting because they can be non-Abelian also. So now this is more or less what I did 10 years ago or something, or longer. But now since then we've made some further progress with Gert. And this turned out to be spectacularly wonderful. So the next thing is that we break permutation symmetry some more. Normally we would have initially an SR symmetry, but we can fix by changing the order of the particles before we start calculating. We can require some nice things. So, for example, we could say require that the second particle, charge number 2, and the charge number 1 is the identity. So we already fixed that. That if I say, oh, let's take the sum over S, let's say with running from 1 to R, and then assume AS. So here merging 2 with S, and then look how many S's come out again. Right? But I can do this with any other particle. It doesn't have to be 2. So I can say, and AR, no, AR, and AQ, whatever, AS. So I kind of require that 2 is the particle such that if I merge it with another particle, most copies with the other particle come out if I sum that over all the particles. This is clearly something I can pick, which doesn't depend on the order in which I present the particles. So it's a good way of picking particle 2, which doesn't depend on the order I already had them. So this picks particle 2. And gives it some special property, which is good because this property I can actually check. Like I can just try and choose ends, and then I check afterwards if it satisfies this property or not. And if it doesn't satisfy it, I can just throw that possibility away, because I know that whatever fusion ring I find, I can always make it have this property by changing the order. So, okay, big particle 2. And then once I have chosen particle 2, that makes it possible to also further fix the order a lot, because now I say, then order the rest. By just saying that, let's see, yeah, the size of N A2 AQ AS. So that means that if a particle has a smaller value of this, it must be further down the order than the other particle that has a smaller value. How to say it? So what I mean is that if U is greater than P is not the number of pairs here, just the number of particle, then N to AQ Q It's going to be less than n. It's particularly useful because if I fix this one first, then I know that later when I choose these, I have to choose them smaller than that one, so it really restricts the search space a lot. Right? And I can actually break symmetry more. If some of them have the same value of this, then I can break it inside that by using the fusion with A3 and keep going like that. So I can really do a lot of symmetry breaking here, and that really helps somehow. But if you want to see the rest, read the paper. There isn't very much more. Actually, it says there are more things you can do, but they're almost too complicated to do. So it's faster just not to do it. Okay, good. So after this, then this was kind of for self-dual particles. You do the same thing for the non-self-dual particles also. After that, then you have variables. And ABC. Of course, we already reduced the set of variables, so keep that in mind. And we have constraints, which are, of course, associativity equations. Associativity is just, for example, sum over f n a b f and f b d. This is if I put A and B together and then the result F is C. This should be equal to having N B C D and A G B. So where I put B and C together first, and then this is a very simple quadratic constraint on the ends. But of course they're integers, so I can't just go solving it without taking that into account. But also the inequalities that I just indicated there, the further constraints. And then what we do is we just want to fill in the unknowns in principle, and but not all of them. We want to fill in as few as possible of the unknowns because there are too many unknowns to fill all the possibilities. So we want to do a smart search. So the strategy is now we can call these constraints C and label them with some index I. So the strategy is find the CI with the lowest number of unknowns in it, because it's the easiest to fill in.
Why is it NAG rather than AGA in that last thing?
Well, A times B times C, these go together to G, and then A and G go together. And G go together to D. So this would be A times N B C D times
Okay.
then we take the sum outside, and then I get A times G.
Yeah.
And then I have to.
Yeah, sorry. Yeah. Right. Okay.
Yeah. Okay, so we find the constraint with fewest unknowns and we fill that in. Well, first of all, and we fill in the unknowns, and the unknowns are, we might write them as V. So let's call this one C1 here. Yeah. That's the first one, fewest unknowns, and these are the C1, the unknowns variables. These are of course the ends, but we just label them if we want to. However many there are in this constraint. So let's say there's L1 of them. Then we fill in these unknowns in the constraints. Of course, if they violate, so we choose values for these between 0 and m, 0, 1, 2. So there's a lot of them, but there's hopefully not too many. Fill them in. If they satisfy T1, then we have to go on from there. But if they violate T1, then we can just forget about filling in all the other unknowns. We already know that this constraint is violated. So, okay. So C1 is violated. Well, then we balance these. At these particular values. If it's satisfied, then we say, well, so we've chosen numbers right here already. All these, if it's satisfied, then we fill the value in all the I, right? And then we find C2, which is the one which now has the fewest variables left, not counting the ones that we just filled in. Now with fewest variables. And these variables, of course, we might call T2, 2, 2, etc. T2, L2. And then we just iterate this. So we fill in those. If it's not satisfied, okay, then we're done with this part of our search tree. If it's satisfied, then we find the next set of constraints, etc., and we keep going. So just a backtracking tree search. You go forward and find more and more deeper branches, as long as you keep satisfying all the constraints. You try to pick the simplest constraint to satisfy, of course, or to violate the one with fewest variables, so the smallest search space. Then if you violate, then you take a step back and you go fill in. If you violated V2 but not V1, then take a step back and you try the next possible entry for these variables in V1, and you keep going. So you exhaust everything.
But in practice, you can only keep going for so long as there is no end to this.
Yeah. So I mean, well, it's a finite search space for any given rank and
You
multiple.
just define that
Yeah.
search space of all of these.
Yeah.
But and how far have you got to go?
Yeah. So this may not sound that amazing, but it is actually amazing. We have been able now, so it's the next step is to show you 3 results. This is unexpectedly efficient, and it's has allowed us so far to find over 28,000 fusion rings. And we can go up to rank 9 for rings with multiplicity most 1. Also rank 8. So for rank 7, multiplicity 2, for rank 6, multiplicity 4, and below that we can even try how high we can go, because it's kind of easy. So controls. More than 28,000 rings found. Of which 353 multiplicity free, which means that they have a maximum 1, and 118 of them are not muted.
Just one back question.
Yeah.
Conformability is provide a set of user rings.
Mhm.
How many of those would be corresponding conformability?
Yeah, I can actually tell you pretty much. I could tell you exactly. It's not a huge
Roughly
number.
is quite sufficient.
Yeah, about 50 or so.
So it's about 50 of conformability is under Leicester and
Yeah, so, well, most of them are, there's a lot of new ones, but of course tend to be higher multiplicity and probably most of them aren't categories. But there are many that are interesting in categories which aren't, but which aren't conformable theories. I might be underestimating 50 a little bit, but it's definitely less than 100. Yeah. I can tell you exactly if you want to know.
you know that's indicative. It's not 27,000.
No, absolutely not. No. Yeah, so we have all the multiplicity free ones up to rank 9. And all with and the 2 up to 7 and that's 4 up to 6 and then we go. I think we went up to 16 for 2 because clearly we know them all anyway, and there's it can be many of them. So, right. So that's one thing. But I should say nobody before this has managed to get past rank 6 at all. Even using much more sophisticated methods, which assumed a lot more about the rings. So this is kind of amazing that something as simple as what I just described actually does it. Then there's an old paper of Kepner and Houston from 1995 which tried to find all the quantum field theories and does it completely differently and which looks like much smarter, but actually they don't find a lot of stuff that we can find. So then of course we put this all together. If you want to see a lot of examples of this, go look on what we call now the Angen Wiki. This is a web page that we host in Loop. If you type this into Google, it will actually go there. But if you want to find an explicit address, it's like www.php.NUIM. I used to NUIM, and then yeah, we've actually find so many of these. We had to come up with a naming scheme for them because there wasn't one for there's this many rings. But I'm not going to get back into the naming scheme, but it's kind of interesting. So think of a good one. And then we found this very interesting result, or well, thing. It's not really a result. We see that the number that's given R and M. It seems to scale as some constant, which depends on M times n is 1 to the power R. If anyone can tell me why I've never even seen this conjecture or anything, but this is
The number of fusion rings.
the total number of fusion rings that's given rank and total maximum of this scale like this. Obviously, there are fluctuations because these are integer number of things, and but it's surprisingly good for all of our data. And the constant depends, so the constant decreases with m. So if I was going to be very calculated, I'd say it decreases roughly 1 over m squared. Because that's 1 0.72, C8 about 0.01. But by that time, this is a large number, so it still grows in. Okay, so that's a kind of mystery. Then if I look at the multiplicity free ones, I can say, okay, let's look at the rank 1, 2, 3, 4, 5, 6, 7, 8, 9. The total number here would be just a equation 1, 2, 4, 10 here, 16, 39, 43, and then 96 and 142 here. So the multiplicity free ones are relatively rare. So that's what the multiplicity free ones. And then there's another little mystery which I don't understand exactly why that is if you have the maximum number of pairs. So if you have rank over 2 pairs, so the return of self-dual, then the number becomes 2 here. It's not in what I'm saying. Well, almost all the entries are 1, which is surprising. So, for example, 3 is 1, and this is 1 and 1. And 6, there are 3 for the reason, and then it's 1 and 1, and 2 here. And for the old cases, 3 and 5 and 7, we weren't able to find any other ones with high multiplicity either. So I don't know why that is so restricted, but for whatever reason, it seems like a.
It's like it's the purely complex case where you have no S equal to 0, right?
Yeah, the only self-dual ones I did, but
Yeah.
And for 3, it's trivial to show this, but for 5, it's something quite complicated, and for 7, I have really no idea how to start. And then the non-Abelian ones start at 6. So non-Abelian and also multiplicity free would be 2 at 6, interesting, and then 3, 7, 19, and 8, and 26, and 9. And these are just the ones that are multiplicity free. The 2 at 6, one of them is just the first non-Abelian group, E3, or S3, and the other one is so-called Hagerov.
Yeah.
I can tell you how it works, but you know, people are getting bored of it. So at 6. At the E3 and Hagerov.
Can you say a little bit more about the hydro model?
Yeah, I can tell what Hagerov does. In fact, there's a whole series of Hagerov does, one for every Abelian group. Tell you a bit more about the other non-Abelian ones too. So yeah, Hagerov Izumi. I think Izumi do a lot of work on this too. So we have an Abelian group, a finite group. Everything is finite. And as usual, the elements of it are included. So equals 8 times h, right? As usual. But this is Abelian, so actually not interesting in that sense. And then we add non-group elements, non-group charges. Let's call them loop G. One for each element of G. And in fact, G is just equals D, where it is the unit element of the group. And then the crucial thing here is that, so, and more generally, you get H times PB HG. But the crucial thing is, of course, the other way, CG equals H. This is by definition, say inverse times CG, which is of course H inverse T. That's where the non-Abelianness comes from. So it only works if the group has elements which are not their own inverse. But that's most groups, of course. And then you still have to see what happens when you multiply two of the t's, dg times dh. But you can sort of figure that out now because you say, oh, well, this is u times dg times h times td, right? And then this h is to come over to this side. So that's dh inverse cd times dg. And then the trick is that TE times TE must be equal to 1 for the unit element of the group plus the sum over TE. And if you take that into account, you know, this word here is actually the H inverse plus the sum over all the you see that these also in general those can do. And that's the whole I'm presuming for all reading groups. Now, of course, the reason that people were really interested in this is because somehow they found it from Norman algebra. Actually, there have just been two big papers announcing that they constructed some field theory that is supposed to have these fusion rules for the expectation, which I haven't read yet, so I don't really know what's in the paper, but it looks interesting anyway. Big groups of collaborators, well-known people, so yeah, there's a lot of interest in that. So that wasn't the one we were most interested in because we already knew that existed. There's a whole bunch of other ones, like I said, and many of them can be summarized as what we have called songs. And we can prove for some of them that they can be made into categories. Songs is short for single orbit, normal, so group extensions. So you see why we need the abbreviation. And the simple idea here is that, okay, these would include, for example, the Haga-Izumi theories and also the Tambari-Yamagami theories for the non-Abelian groups. But they have more things. The basic thing is that you have some group. I'm not going to give you the full definition because it gets a bit messy, because we actually tried to sort of prove that this was the complete class of objects with a certain property, and then you end up with a bunch of structure that is just a bit messy, but it works. But at least we have a group G. And it can be non-Abelian. Then on top of that, we have some extra set of objects. So we have extra charges, which you might again label with T's, right? T1, T2, etc. And these charges form a single orbit under the action of the group elements fusing onto them. single orbits under flat diffusion. So basically, I can pick one of these and then multiply it from the left with some element of the group. For all I, then there is some. So this is true. So hence single orbit, and then you also require that the stabilizer in the group is a normal subgroup. So the stabilizer S, which is all elements H in G, such that H times Ti for some particular Ti is a normal subgroup.
Sorry, so it's not a stabilizer for a particular TI, you said, or
Yeah, you pick one. It doesn't matter because they're all actually
like
I'd say it's isomorphic.
okay.
So if there's one of them is normal, they're all normal. But in fact, they might all be the same. I have to think about that. Okay, so that's a normal subgroup, and if you have these three things, then we classified all these things. At least we were able to characterize them all. There's a few bits of the characterization that was for individual groups. You have to figure out what they are essentially. But you need some automorphism of the quotient group of G modulo S and things like that. But I just give you one example, which isn't Hager-Prezumi or Tsumbari-Yamagami example. Take the group B3, and we have two elements of the group, two extra elements. Let's call them T and TS, and it's probably useful to write it as B3 is. We have two elements S and T that generated with S squared T to the third. It's identity, so triangle as mirroring the triangle, and T is rotating the triangle. And this has a normal subgroup, which is at 3, just generated by T. And then what we can do is here we will have fusion rules. Well, D times H is for H, and this is already non-Abelian because it could be non-Abelian. Right? For any elements in D3, and then R to the power A times TE is R power A. Yeah, it's TE. Power A times TS is TS. So basically, these elements of the normal subgroup are stabilizing the other elements, like I was saying, normal subgroup stabilizer. But if I go with the rest of the group, S R to the power A is the other three elements times TE, that will give me TS. So units of that. And finally, TE times TE is just the sum over in the Z3. So R E plus R plus R squared, and TE times TF is ds times db is also equal to ds times ds. And this is equal to s times the sum over the 3. So basically, all the non-Abelianness comes from the group itself. So it's kind of a little bit boring, but the crucial thing is that we can actually prove that this thing becomes a tensor, proper tensor category. So there are F symbols and everything for this. So and we can also, if we want, as n times the sum of all the t's. Then that will still work. And it's all, and so this is just a very simple example. So you might say, why don't I see anything like this inverse? It happened for the Haber-Bizumi. And I took an element from one side to the other with the t's. So more generally, you would have an automorphism. If I say t times g, which would be an automorphism of the quotient group times times t. Okay. And the automorphism happens to be the inverse in the case of Haber-Bizumi, which is an automorphism there because it's an Abelian group. Normally that wouldn't work, but here it works because it's Abelian. And there's another bit of structure which I don't know what to mention, but but this is a bigger class than I'm saying, but you get the idea. And basically, whenever you have one orbit and it behaves reasonably okay, then you can figure it all out, and it's great. But there are actually way more examples with anything with multiple orbits, and you can have the different left and right orbits under the fusion with G, and they might interlink with each other. So you have orbits that are only intersecting at part of the orbit. It's just the most terrible things writing. All right, so now I have another bunch of pages about what happens if you want to do stuff with categories.
Yeah, that would be the question, yes. Maybe you can just tell us how many of these 28,000 into categories. Or do you know?
No, that's the problem. So we know pretty much completely which ones, well, not completely, but almost completely, which of the multiplicity free ones are tensor categories, because we have lots of techniques now to figure that out. And to actually construct the tensor categories. That's a big piece of the work with Gert. But as soon as you have multiplicity, it becomes very much more harder. And of course, most of those 28,000 have multiplicity. And we can exclude some of them, several thousand, by various criteria as to things that they must have to be tensor categories. But we're still left with at least 15,000 or so where we don't know. So if anyone can think of better criteria to immediately decide if something can be a tensor category or not, that'd be pretty great. We have some particularly interesting ones that mathematicians are interested in, because you can, for example, say that the fusion ring is simple if it doesn't have any fusion subrings. So people like to think about these. It's like simple groups. So we found a couple of these and we still don't know if they're actually categories. So yeah, but there's people actively working on that.
Why are tensor categories important?
Again?
Why are tensor categories important?
Yes, so that was the next part. If I have more time, I can tell you why tensor categories are important. If you need to go somewhere, let's do it.
But yeah, so I was going to ask a question about the thing you just said before that. Yeah, where you went to tensor categories. Do you already know that kind of classification of all these fusion rings into products are something simple, fusion rings that you would maybe?
Yeah, I don't think there's even results like that, like you have for groups that people say, oh, we can just write it as some kind of, semi-direct product of simple ones. Of course, we have tools now that where if you give us a fusion ring, we can immediately test if it has sub rings or if it's a product of things. But for small fusion rings, but in general, it's I'm not aware of very strong results in that area. So, but I think mathematicians are thinking about it anyway. It's a natural thing to try to replicate.
Just got to run on. Yeah, thanks.
Should we maybe have a 5-minute break for people who think, people to leave if they want to, and then or go to the toilet?
How much break do you want?
It doesn't have to be that long. I can do this bit probably quite quickly.
I'll always get notice to that.
It's always possible, yeah. I could do, but that could be interesting actually. But I don't know when you want that.
You don't want to similar schedule for next week if you want to continue.
In principle, though, if anyone else is still interested.
I'll take that. Yeah, that would work.
Yeah.
Okay. If I know you're very busy, so I'm not.
I'm thinking, I have something Thursday already, but I think I should be okay for this Thursday anyway.
Okay, then let's do it.
Yeah, so then I just give you the other, hopefully 1 hour at most of these notes, and you'll find out why tensor categories are interesting.
Yeah.
Great. Thanks everybody for coming. And we'll do that.
Yeah, that was great. Thank you very much. That's it. Very interesting. Thank you very much. I'll try next week. Yeah, but here is even more coverage here. Great camera work, Kevin.
Get job out of you.
There's a problem about the mark. Ross. Yes, OWSP1.
He doesn't think I know him.
Sorry?
So I didn't know him, but now he made me for sweet.
Hopefully you can see the picture of it together seconds.
Yeah, faces are easier.
There's this camera off.
Yeah.
All
Right.
where are you located, Mark?
No, it's not.
Okay. I'm going to stop the recording.
Yeah, it's good.
Yeah.